Hello Internet. In this video I will give an overview of how analog circuit simulators work, and I will showcase the circuit simulator I built, MadCSim. We need simulations because it's much more convenient and cheaper to run a simulation and experiment with the design and variables before committing to building a prototype, thus shortening the feedback loop and speeding the development process. We use mathematics to build a model about the physical phenomena we're trying to study. A model is just a set of laws that describe the behavior of the phenomena based on variables and constants. In turn, we use this model to predict the outcome of the phenomena based on an initial state. It's nearly impossible to solve physical models for large-scale cases using analytical methods, due to the huge effort it would take to apply the model equations on all the elements of the system and take complex geometry into account, let alone solving these equations analytically. That's why we need to use computational methods to solve these systems, turning complex analytical steps into a more simple computational algorithms. For electronic components, we can represent a circuit as a collection of components centralized in a single point, and their behavior can be described by idealized mathematical models and connected together by wires with zero resistance. This is called the lumped element model. It simplifies the circuit to a manageable form such that the resistance of wires, propagation delay, parasitic resistances, capacitances, and inductances are all ignored. This may cause mismatch between the simulation and the real world, but it isn't a big problem as we can add the mentioned aspects as components like parasitic capacitance, for example, if we want to take it into account and get a more accurate simulation that better resembles the real world behavior. Assuming we have a circuit represented in a lumped element model, how can we simulate its behavior? Well, we have to determine what variables are we measuring. In this case, we are measuring voltages at nodes and currents going through components. Then we have to apply the model equations to find these variables. For each component, the current going through it is related to the voltage across it by an equation based on its mathematical model. Also, Kirchhoff's current law states that for any node, the sum of currents flowing into the node is equal to the sum of currents flowing out of the node. Thus, we can use a technique called nodal analysis, which simply applies Kirchhoff's current law at each node in the circuit while substituting the current going through each component by its mathematical equation that links the current to the voltage, thus making every equation as a function of voltage, the unknowns. Doing that on every node will give us a system of equations that is exactly determined. That's because we have n nodes, thus n unknown voltages, and n equations from applying Kirchhoff's current law at each node. Hence, the system is an n by n system. Let's consider the following example. We have a 2 amp current source pushing current through a 20 ohm resistor in series with a 10 ohm resistor. We need to know the voltage V1 and V2. Let's apply Kirchhoff's current law at node 1. We have the current going in is the source current, which is Is, equals to the current through the resistor, which is given by Ohm's law as V1 minus V2 divided by R1. We can simplify the equation by replacing 1 over R with G, which is the conductance. Now we apply Kirchhoff's current law at node 2. We have the current going in as the current through R1, which is V1 minus V2 times G1, equals to the current going out, which is the current through R2, V2 minus V0 times G2. We have V0 is ground, which is 0. Simplifying the expression, we get this equation. Let's express this system of equations in matrix form. We will get this system. Then substituting with the values of G1, G2, and Is, we get this system. Then solving this system, we get V1 is 60 volts, V2 is 20 volts, which is correct. Now let's check in MadCSim. We have the same circuit in MadCSim. Now let's run a DC simulation. Let's probe V1 and V2 and check the results. For V1 we have 60 volts. For V2 we have 20 volts, which matches our solution. The system of equations resembles Ohm's law, but in matrix form. We have the conductance G multiplied by the voltage V equals the current I. Hence, the coefficient matrix G is called the conductance matrix, and the constants column matrix is called the current source column matrix. Also, the unknown column matrix V is the voltages. Now, let's consider a more advanced example. We have replaced the current source with a voltage source of 60 volts, which should yield the same results. But we will find a problem applying Kirchhoff's current law at node 1, as we don't have an equation of the current coming out of the voltage source, as it depends on the load connected to it. We can modify the nodal analysis method, hence the name modified nodal analysis method, to add a new variable for each branch current that is unknown, and add the component mathematical model equation as an extra equation in the system. That way, the system remains exactly determined. The new system will have variables n plus m consisting of n node voltages and m unknown component branch currents, and equations n plus m from applying Kirchhoff's current law at each node, and an extra equation for every unknown component branch current. Let's construct the system of equations, but now we will start with the system represented in matrix form and fill out the empty values as we go along, handling one component at a time and adding its contributions at each node directly to the system of equations in matrix form. Now we have row 1 is Kirchhoff's current law KCL at node 1, row 2 is KCL at node 2, row 3 is the voltage source equation. Now we have the contributions of R1 at node 1 as G1 times V1 minus V2. At node 2 it's negative G1 times V1 minus V2. Then we have R2, which only contributes at node 2 as the other node is ground. We have its contribution at node 2 is G2 times V2. Now let's go to the voltage source, but notice how the system of equations has a new unknown, which is IS, the unknown branch current of the voltage source. We have the voltage source contribution at node 1 to be negative IS. Now we add the equation of the voltage source at row 3, which is V1 equals to V, the value of the voltage source. Substituting with the values of G1, G2, and V, we will get this system of equations. Solving it, we will have V1 is 60 volts, V2 is 20 volts, IS is 2 amps, which is correct. Let's confirm in MadCSim. Now we are in MadCSim with the same circuit. Let's do a DC simulation. Probe node 1, it's 60 volts. Node 2 is 20 volts. IS is 2 amps. Because the system of equations is exactly determined, it has a unique solution. But I won't get into the mathematics of solving linear systems in this video. All that was to solve the circuit at DC or a single time point. But if we want to see the behavior of the circuit with respect to time, we have to solve the circuit at each time step, making sure to choose an appropriate time step, small enough to capture the transient events, but not too small to increase the simulation time. Some components need special handling as they are time-dependent like capacitors and inductors, or nonlinear components like diodes, transistors, and MOSFETs. We can also use different models for components to perform AC analysis, but I won't get into that in this video. If you want to learn in depth about circuit simulation, I recommend Electronic Circuit and System Simulation Methods book. It's a great book with lots of in-depth information about circuit simulation. I have implemented these techniques and more in MadCSim Circuit Simulator. You can perform DC operating point, transient, or AC simulation with a straightforward schematic editor and a small collection of components. You can try it on your browser at this link, or you can download the desktop version from this link. That was it for this video. I hope you enjoyed. Goodbye.